Okay, so today we're going to talk about how rotational motion is quantified. So first we're going to talk about the difference between rotation and circular motion. So for circular motion, then the object itself travels in the circular path, where with rotation, the object spins around an axis inside itself, and it actually rotates. So let's talk about some vocabulary. Again, translational motion, everything we've done so far has dealt with translation motion, and that's where an object can move all over the place, but it can't flip, spin, turn, or anything like that. Now we're finally allowing our objects to rotate. A rigid object is an object that keeps its shape even when it moves. An example of a non-rigid object would be like a pool noodle. When you swing those things around, they start bending all over the place, and that's just a little too much mathematics for us to worry about. So we're going to assume that everything we talk about is a rigid object. And the axis of rotation is the imaginary line that goes through the center of an object about which an object spins. So all the points spin around that axis of rotation. So what's going to happen is we're going to have kinematic equations, like V final equals V0 plus AT, except we're going to have them doing rotation. And in rotation, we're going to have new variables for velocity and acceleration and displacement. So what we're going to do is we're going to make a chart of all these new variables and quantities and how they relate to the old ones, just to help us make that connection. So when we compare our rotational analogies and we'll get our kinematic equations, the old quantities that we will compare to, we had displacement, which was x. We had velocity, which was v. We had acceleration, which was a. And we had time, which was t. And time is actually going to stay as time. We're not going to change anything with that. So the symbol for time is going to be t. That's pronounced T. The units we will use is seconds, and of course, just time would equal time. So instead of displacement, x, we're going to use angular displacement. And the symbol that we use for that is going to be theta, which is theta THETA. And the units for our angular displacement, we could measure angles in degrees or radian, and we're going to actually use radian because it's going to make things a lot easier by using radian. And the connection, how do we get from the old to the new? Well, you've actually used a special case of this equation a long time. If I go through the angle measurement all the way around a circle, my displacement or my distance that I travel is the circumference, and you have often used circumference equals 2 pi r. But that's a special case. We don't have to go all the way around. So what we can do is we can look at this and we could say that the distance that we travel, x, instead of 2 pi being our distance in radian all the way around, we can just say that it's theta, some random distance, times the radius. So x equals theta r. So our connection for displacement and angular displacement is just x equals theta r. Instead of our old quantity for velocity v, our new quantity is angular velocity, and the symbol for angular velocity is the lowercase omega, and it has curvy bottom. Don't do a pointy w. This is an omega with a curvy bottom. And the units, just like velocity was meters per second, our units now are going to be radian per second. And our connection will be the same. We'll follow the same pattern, that the velocity is going to be omega times r. And our new quantity for acceleration, you may be able to guess this, is angular acceleration. And our symbol is going to be a Greek letter alpha. And again, just like we did with radian and radian per second, the angular acceleration is going to be radian per second squared. And following our connection pattern, the acceleration of an object is going to be alpha times the radius. To give an example of this, we're going to use Usain Bolt versus the Flash in a race. And what we're going to do is we're going to have them race around this tire. So what we can do is we can give the wheel a little spin, and we can see who gets around first. And as you notice, each lap, Usain Bolt and Flash are going to tie. And that's because their angular displacement is the same. They both go through one full rotation in the same amount of time. But who goes further during a lap? Well, when we look at that, when we talk about their actual displacement using our conversion of x equals theta r, you would see that Usain Bolt's distance that he travels is greater because when we do theta r, Usain Bolt has a greater radius. Now what I'd like you to do is develop the rotational kinematic equations. I'll do one with you and then I'll let you do the others on your own. So the idea is that we have our kinematic equations and we have V final equals V0 plus AT. And what we're going to do is we're going to take the rotational analogies and replace them in with what we have. So if we look for V, we're now writing omegas. So here for V final, I'm going to write omega final R equals omega initial R. And then if you notice for alpha, we're writing, or for acceleration, we're writing alpha R. And then this is times T. So we do times T. And if you notice, though, we have an R in each term, so we can actually divide through by R. For our angular motion, it doesn't matter what your radius is. We're just talking about how quick we go around, and we saw the example with Usain Bolt and Flash, and they go around in the same amount of time. So this equation then would actually come out to be omega final, which is our final rotational speed, equals omega initial, our initial omega rotational speed, plus our angular acceleration times the time. So go ahead and take a moment and do the equations for delta x, v final squared, and we even have an equation for v average. So make those equations using the rotational analogies. Remember, our delta x equation is delta x equals v0t plus 1/2 at squared. And using our rotational analogies now, delta x, instead of that, we're using theta. So we have delta theta equals, instead of v, we're using omega. So we have omega 0. T, remember, stays the same. Plus 1/2 will stay the same. But instead of a, we're using alpha. And then we have t squared. And notice that I didn't put the r's in this because I knew that as we went through, they would just cancel out anyway. For our v final squared equation, remember we have v final squared equals v0 squared plus 2a delta x. And again, if we use our analogies, instead of v final, we have omega final squared equals omega initial squared. And then we have plus 2, that hasn't changed, alpha delta theta. And again, we didn't use r's, but it might be a little more confusing this time. But if you think about it, omega final squared would have 2 r's in it because it would be squared, so r times r. Omega initial has r times r. Alpha has an r, and delta theta has an r. So r's would cancel out again. So we'll box this off, and then we'll go look at our last one. Remember v average, when we did that before, we said that as long as we have constant acceleration, the average velocity is the average, add up the final and initial, and divide by 2. So if we do that using our rotational analogs, instead of v, we're using omega. So this is the average angular velocity is the final angular velocity plus the initial angular velocity divided by 2. So those are our rotational kinematic equations, and we'll use those just like we did before. And remember, as we said, acceleration needs to be constant. Well, for this, then the angular acceleration, alpha, must be constant, or we can't even use these. So let's look at a sample problem. We have a disk rotating, and let's say that it's going 27 radians per second and has an angular acceleration of -3 radian per second squared. And we want to know what is the angular velocity after 8 seconds, and also how many rotations has it gone through. So if you remember how we solved kinematic problems before, we used our little table where we had V final, V0, etc. So now we're going to do omega 0, omega final, alpha, delta theta, and t. And we take a look at what we know. So from the problem, we can see that the initial angular velocity is 27 radians per second. The angular acceleration is -3 radians per second squared, and the time is 8 seconds. And we want to know omega final and delta theta. So I think what equation has omega 0, omega final, alpha, and t in it? Well, that means I can use omega final equals omega 0 plus alpha t. So omega final equals omega 0 was 27, plus alpha was -3, and t is 8 seconds. So that means omega final is going to be 3 radian per second. So I can figure out, what the final angular speed of that would be. Then it wants to know how many rotations did it go through. So I could say that delta theta equals omega 0 t plus 1/2 alpha t squared. So delta theta is omega 0 was 27 times the time of 8 seconds plus 1/2 alpha is -3 times our time of 8 seconds squared. So delta theta becomes 216 minus 96. So delta theta is 120. And remember, our units for theta are radian. But that's not what the problem asks. The problem says how many rotations. So now we got to do a little conversion. We have 120 radian. And we know that there are, in one rotation, is 2 pi radian. So my radian units cancel out. So I have to do 120 divided by 2 pi, which comes out to just over 19.1 rotations. And again, just always make sure that you look back and answer the question that's being asked. So in summary, solving a rotational kinematics problem, maybe you'll use, omega final squared equals omega initial squared plus 2 alpha delta theta. Is not much different than solving a linear kinematics problem where things just move in a straight line, except now we just have cooler looking variables and it makes you look a lot smarter. But you still do the same techniques. You still do your variables, you write them down, omega 0, omega final, alpha, delta theta, t, and the same trick that we need to know 3 things, and then we can solve for the other one using our equations.